So I'm Rupert. I'm talking about fair public decision making. This is joint work with my advisor Vince and Nisarg Shah. So the idea of this work is to apply ideas and techniques from the theory of fair division, which generally works with dividing private goods, and apply some of that to making public decisions in settings like, for instance, choosing the location of a public facility, or just something like choosing where to go for lunch with your research group. So the sort of setting that we have in mind is this one where we have a couple, Alice and Bob, and they sit down on Sunday and plan out their activities for the week. The following week, Monday through Saturday. And just to keep the example simple, let's suppose they're choosing from a menu of 2 activities per day. And each of Alice and Bob has a utility for each activity. So if we just look to Monday, Alice has utility 3 for playing soccer, 0 for video gaming. Bob has utility 1 for soccer, 4 for gaming. Okay, a couple of things that I just want to point out. First of all, they're making decisions for the whole week with all the information up front. So this is an offline problem, not online. The other thing is that we're going to insist on deterministic outcomes. And I'll say a little to randomized outcomes at the end of this time. So they make some decisions about the activities that they're going to do. Perhaps they choose these. So now how do we define the utilities for each agent? Well, it's just additive. So Alice's utility is 3 for Monday, 2 for Tuesday, 3 for Wednesday, and so on, for 13. And Bob gets 23 utility if we add his up. All right. So a little notation that I'm going to need in this talk is N is going to denote the number of players, or I might call them agents. M is the number of issues. And just to be very clear about what all these things are, Bob and Alice here are players. So these are kind of the players in the game. The issues here are the days of the week. So for each issue, we have this utility matrix. And then the individual options or activities are alternatives.
All of them have to do the same one?
They all have to, we choose one alternative and they all take part in that. Yeah, that's right. And I said game, I probably shouldn't have said that because we're not going to be considering strategic aspects. Okay, so I said we're going to look to use ideas and techniques from private goods division. And one thing that helps us do that is that our setting generalizes private goods division. And the way to see that is with this. So maybe Alice and Bob's relationship has soured, and now they need to allocate, distribute the items that they own together. So like the house, the car, the TV, and the cat. And now each issue is an item. The alternatives for each issue are who gets the item. So we have Alice gets the house, Bob gets the house. And what defines this as a private goods division problem is that all off-diagonal entries are 0. Right? And that just says that if the item goes to Alice, Bob doesn't get any utility, and vice versa. Then the on-diagonal entries are the value that each agent has for the item. Right, so this is the private goods setup, and if we allow non-zero entries on the off-diagonals, then we get the public setting. Okay, so that's our setting. What would we mean by a fair solution? Well, the prominent notion of fairness in private goods division is that of envy-freeness, and its relaxations like envy-freeness up to 1 good, which basically say that no player should envy another player's allocation, in that they shouldn't want to trade their bundle with that of the other player. And as has been observed before, this no longer really makes sense for public decisions, because if Alice and Bob are both playing soccer, what does it really mean for Alice to envy Bob? It's not as if she wants to trade places with him, because she'd still be stuck playing soccer, which she doesn't want to do. So instead, we look to proportionality, which has a more general definition that still applies. And that is that each player should get a 1 over n fraction of the value that they would receive for being the dictator. So if we go back to our example, now I've just circled in red the utilities that Alice could gain if she could choose the activity every day. And her proportional share is simply the sum of these divided by 2, which is 8 in this case. Okay. Turns out that for deterministic allocations, proportionality is still too strong, so we still can't guarantee this. So what we do in this paper is we introduce 3 novel relaxations of proportionality, which of course still make sense in the public setting and by extension the private good setting as well. So the first one is the round robin share, and to explain that I first need to introduce the round robin mechanism. So the round robin mechanism is very simple, just works by fixing an ordering of the players and have the players take turns choosing the outcome on an issue whose outcome hasn't yet been determined. So in our example, suppose that the ordering we fix is Alice, then Bob. So Alice chooses, Bob chooses, Alice, Bob, Alice, Bob. So Alice gets to choose first, and she says, thinking completely greedily, what alternative can I choose to get the most utility? And that is to choose ice skating on Wednesday for 5. Then it's Bob's turn, and if you look at this, so Wednesday's chosen. Now for Bob, he can do the best by choosing golf over here on Friday. Now Friday's chosen, and we can keep going like this. Alice chooses, Bob, Alice, and Bob. So this defines some outcome. And this inspires us to define the round robin share. So the round robin share says that each agent should receive the utility guaranteed to them under the round robin mechanism, assuming that they receive 0 utility from issues that they don't choose the outcome of. So this is this is more like Alice playing in the round robin mechanism against some adversary who has the power to impose an outside option that Alice doesn't like at all. And in that sense, it's kind of the weakest axiom that we could possibly define that's still inspired by round robin. So you could perhaps think of ways to strengthen this, and most of our positive results would still hold, depending on how you choose to strengthen it. But as we'll see, even with this weak version, it's still hard to satisfy this property in conjunction with others. So this is the one that we go with in this work. And just to see how this works, to compute Alice's round robin share, I've circled her most preferred alternative for all these options. The way it would work is in the worst case, Alice is going to go second in this round robin ordering. So we order these alternatives, these issues, by how much utility Alice could get if she were to choose the outcome. So this one is first just because 5 is the highest number here, all the way down to her least favorite one, because 1 is the lowest. And we say the adversary gets to choose the first outcome, so that's a wash. For her second issue, Alice gets to choose. The third's a wash. She gets to choose the 4th and the 6th. Right, so we add these up, 3 plus 2 plus 1, her round robin share is 6. Note that this is lower than the proportional share, which was 8. Okay, that's the round robin share. We've defined one further relaxation of this called the pessimistic proportional share. And this says that each agent should get the utility guaranteed by choosing the outcome of the same number of issues as before, but now they're M over N worst issues. So instead of being allowed to choose the outcome on issues 2, 4, and 6, now we're just saying to Alice that she gets to choose the outcome on 4, 5, and 6. So the adversary gets 1, 2, 3, Alice gets 4, 5, 6. So her pessimistic proportional share, or PPS, is 5. Okay, and one more is proportionality up to 1 issue. And this definition is inspired by envy freeness up to 1 good in the private goods literature. And it says that every player I should achieve her proportional share by changing the outcome on at most 1 issue. So now I'm going to just think about Bob for a second. His proportional share is 16. I haven't worked that out, but you can easily. So say we choose some outcome. Here it is. And if you look at Bob's utility here, it's 11. So that's not his proportional share. That's okay. We know we can't guarantee that in general. But if we think about changing Wednesday's outcome from ice skating to basketball, Bob now gets 8 utility here, and his total utility increases from 11 to 19, which would give him his proportional share. So this says that the original outcome was a Prop 1 allocation. So how do all these things go together? Well, fairly obviously, proportionality implies proportionality up to 1 good, and maybe not quite as obviously, but it's still easy to see that proportionality implies round robin share, which in turn implies pessimistic proportional share. So I've given you 3 fairness properties. I know this is quite a lot, but it could be worse because you could get late night emails from NISAG that look like this, followed quickly by updates that get progressively more complicated. Now we have these 3 new fairness properties. We look at, can we satisfy these properties? And if so, how are we going to do it? So first thing is that the round robin mechanism satisfies all 3 of these fairness properties. Fairly trivially in the case of round robin share by definition. And it's also pretty easy to prove that the round robin share satisfies prop 1 as well. But we're not particularly satisfied by this because the round robin allocation might not be Pareto optimal, in the sense that we might be able to find another allocation which makes everyone better off. So it's kind of a minimum standard of efficiency that we'd also want. The intuition for this is just that the round robin solution is so constrained. For instance, it can only choose activities which are some player's favorite activity. It will never choose kind of a compromise activity which might make everyone quite happy. So kind of the goal for this part of the talk is to achieve round robin share and Pareto optimality and prop 1 plus Pareto optimality. So starting with the round robin share. First note that the round robin share just defines a fixed utility threshold per player. So if we start with any outcome that satisfies the round robin share, like the round robin outcome, and then we simply make Pareto improvements on top of this, not worrying about how we might find these, we'll eventually arrive at a solution which still satisfies the round robin share and is Pareto optimal. We can also think, kind of apply the same intuition, but think about doing it in one shot by saying, let's maximize some sensible objective under the constraint that every player receives their round robin share. So one thing, for instance, we could do is run the Lexi-min mechanism. Lexi-min is just maxi-min, so maximize the utility of the worst off agent, but with lexicographic tie breaking. And this satisfies round robin share and Pareto optimality. And of course, by extension, PPS as well, because it's strictly weaker. Okay, so that's fine for round robin share. For proportionality up to one issue, it's not so obvious because just because we take some outcome that satisfies prop 1, it's not clear necessarily that a Pareto improvement on this will still satisfy proportionality up to one issue. And this is because whether or not an outcome satisfies this property depends very crucially on the exact structure of the outcome. Just like envy and envy freeness in the private goods case. But we had some intuition that because we know that the maximum Nash welfare, which is just the product of all agents' utilities, satisfies envy freeness up to one good in the private goods case, maybe it satisfies prop 1 in our public decisions. And indeed it turns out to do so. I won't go through any proof intuition, but it's very similar to the proof that max Nash welfare satisfies EF1 in the private goods case. Okay, so a summary of this section. There's some approximation results there that I haven't mentioned, but they're all in the paper. And kind of this, if you look at this, it gives us one very natural open problem, which is, can we achieve round robin share, proportionality up to one issue, and Pareto optimality at the same time? So we can get any two of these via the three mechanisms that I've described. We don't know if it's possible to get all three at once, or how we would do that. So in the kind of 5 minutes I have left, I'm just going to talk about computing these fairness properties. And once again, we can get the fairness properties on their own without efficiency by just running the round robin mechanism. This is clearly a polynomial time mechanism. So if we want Pareto optimality as well, for PPS, pessimistic proportional share, we have a hardness result. So at NP hard to find an outcome satisfying PPS plus PO. So just a quick note, this is the search problem. It's hard to find one. The decision problem of whether or not one exists is always easy. We've established that the Lexi-min mechanism does this. Right, I think I'll skip the proof idea. And of course, as a corollary, we get that it's NP hard to find an outcome satisfying the round robin share and PO as well, since this is a stronger property. Okay, in the private goods case, we actually have a polynomial time algorithm that lets us find a solution satisfying PPS and PO. And the way it works is it produces a solution that maximizes weighted welfare. So it gives every player a weight and then maximizes the weighted sum of utilities. And this implies Pareto efficiency. And assigns each player a roughly, well, think of it as exactly equal number of items. And this instantly implies the PPS property. So we tried to extend this idea for finding a round robin share and PO allocation. This turns out to fail because there actually exist instances in which no weighted welfare maximization satisfies the round robin share. I don't have it, but it's kind of a simple example which is quite illustrative. Then we tried to apply the same idea for proportionality up to one issue and Pareto efficiency. And this seems to work in all of our simulations, but we don't have a proof either that it works or that it runs in polynomial time. So a summary of this section. We have this rather sparse table for public decisions and private goods, and each of our 3 combinations of axioms. So we have our 2 hardness results and our 1 polynomial time, and this gives us open problems 2, 3, and 4. Okay, so just wrapping up. I promised a little about randomized outcomes. In the randomized case, as we've heard from Samina before, Max Nash welfare for randomized allocations does a lot of really nice things, and it seems fairly uncontroversially to be the right thing to do here if we are allowed to randomize, and satisfies in particular a core property which implies proportionality and all of our fairness axioms. One interesting direction would be to think about whether we can define a generalization of envy or any envy-like property in public decision settings. And I have a couple of related work bullet points, but maybe I won't say anything about them, and we can chat if you're interested. All right, thanks very much.